these three guys. We're going to look at complementary probabilities, conditional probabilities, and tree diagrams. And then we'll move on, look at some other questions. They get more and more detailed as they kind of progress through. So, suppose you have an event A and the probability of it happening is 3/7. Then the probability of A bar, that's how you would say that, A bar, is 4/7. This A bar is called the complementary event of event A. So imagine A was that it rained. Then A bar, the complementary event, would be the opposite of raining. So I guess I would call that dry. Suppose A was the probability that I pass a test, then A bar would be the opposite of that, which would be that I fail a test. And there's a lot of situations where you can kind of break the story into the positive A or the opposite of it, the complementary A bar. If you look at these two guys, if you add them together, you always get 1. And that's how we figure out who the other guy is. So if I said to you, the probability of A was 7/11, then the probability of its complement, A bar, would be, well, whatever's left, 4/11. You see how that works? It's really quite straightforward. If you know A, you can find its complementary probability. Oops, a couple more people arriving. How about, well, this is question 2 from the homework. All right. How about finding that when I tell you that guy? Should be able to work both ways, shouldn't it? So if I know this is going to happen 5 out of 17 times, won't this happen the other 12? And that would be the answer that you put in your homework. Now, you get probabilities that involve counting. And a term that I use a lot and gets used a lot is also called sample space. And basically, you write down and count all the different ways something could happen. Now, there are some situations where that is physically doable, and there's others where it's not. So I'm going to show you an example of 2 questions, one where you could do that and the other where it would be impractical. Suppose we had 3 coins. They're going to be tossed in the air. And what's the probability that at least one of them is a head? Now, 2 distinctly different ways of doing this. First one uses counting and a sample space. So if you throw 3 coins in the air, there are 8 things that could happen. You get 3 heads, 2 heads and a tail, which can happen in 3 different ways. A head and 2 tails, which can also happen in 3 different ways. And lastly, 3 tails. So we call this the sample space. So let's just call that whole thing A. So the probability that you get at least 1 head is out of the 8 things that are happening here, how many of them are at least 1 head? Well, that one's got at least 1. Those have at least 1. And that's got at least 1. It's got 1, but it's got at least 1. And altogether, I get 7/8. So the probability that you get at least one as a head is 7/8. And that works perfectly fine. Here's another way of getting the same question.
What does the sample space look like if you only have two? Like, is there a way to look at it if you have 2 or 3 or 4? So
Yeah,
that when you're making your sample space, because I feel like I'm writing a whole jumble of stuff and I'm like, I don't know when to stop.
Okay, let's talk two things. First, how do I know how many are in my sample space so I know how to stop? And secondly, how would I write them down? You know, so I don't miss one or whatever. Right. Basically, if they're doing a 2-coin one, there's 2 ways of getting the first coin, 2 ways of getting the second, so there's going to be 4 of those. This is a 3-coin story. 2 ways for the first, 2 ways for the second, 2 ways for the third, so that's 8. So that's how I know there's 8 in this sample space. If I was doing a 2-coin story, there would only be 4. I could even tell you what those are. You get 2 heads, a head and a tail and a head, or 2 tails. Do you see that's the 4 things that would happen? Now, how do you make sure that it's not just a jumble and just, because you can probably guess about half of them really quickly, but if you do it that way, you're really going to have a problem. So I tend to do it systematically. So I start with 3 heads. And then I say, okay, how about 2 heads and a tail? And I write down all the different ways 2 heads and a tail can have. Do you notice that the position of the tail is really the easy one to distinguish them? And then I say, okay, I've done 3 heads, I've done 2 heads. How about 1 head? Well, 1 head and 2 tails, 1 head and 2 tails, 1 head and 2 tails. There's 3 ways that can happen. Right, so I've done 3 heads, all the ways of getting 2 heads, all the ways of getting 1 head. And I guess you could say no heads, but isn't that the same as 3 tails? So you'd set it out in a kind of very systematic way, right? Do all of one. Right? You could do, you know, imagine it was a 3-children family, right? You might say 3 boys and then 2 boys and a girl, right? And 1 boy and 2 girls, right? And so on, and then finish with the 3 girls. Now, there is a second way in which we can calculate the probability at least one is ahead. Let's call that event A. Sometimes it's easier to find the complement of A. So what you need to think about here, I'm going to just mute things again. Because Amelia coming in, she can make it. What you got to think is the complement is the opposite of that. So what's the exact opposite of at least one is ahead?
Is it at least one is a tail or at least one is not a head?
So you're still going to use the word at least. Yeah. No, it doesn't work that way, but I understand why you're thinking about that. If I went and said at least one is a head, does it not mean 1 head, 2 heads, and 3 heads? So what would the opposite be? Oh, it'd be no heads. So the opposite of at least one is none. So the opposite of at least 3 days it rains, the opposite is none. It doesn't rain at all. Now, how many of these don't have any heads at all? Just that guy, right? Which is 1/8. How do you get the complement to help us? If this is 1/8, won't that be 7/8? Right. I don't find the one that I'm being asked to find. I find it's opposite, it's complement. And it's easier to get this one than it is that one. I mean, you still do a thing, but one of them leaves 7, 7 leaves you 1. Here a better example, perhaps. I want the probability that I choose out of all the numbers from 1 to 100, right? What's the probability that I choose a number that is not a multiple of 5. This question is a version of 3. Okay, now I could do counting on that. I guess I could do a sample space. I don't want to, but couldn't I write down 1, 2, 3, blah, 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 finish at 9, then maybe finish at 10, then do 11 and 12 and finish at 20. I do not want to have to write down 100 numbers so I can count all the ones that are not multiples of 5. Right? There's a lot of them. So turn the question on its head. What's the opposite of not being a multiple of 5? It's a kind of double negative thing.
A multiply of 5. Oh,
Right.
is that right?
Correct, a multiple of 5. Now, I'm going to find that answer, and because it's the complement of that, whatever this answer is, can't I figure out that one from it? Now, I think I can do all the multiples of 5 without having to write them all down. 5, 10, 15, 20, 25, 30, 35, 40. Can you trust me that there's 20 of them? Wouldn't it be 5 and then 10? Wouldn't it be 15 and then 20? Can you imagine when I got to 100, there'd be a 95 and there 100. Wouldn't there be 2 in each of these rows, 10 rows, 20? So the answer is 20 out of 100. So what's the probability then that you choose a number that's not a multiple of 5? 80 out of 100. So you see how I made my counting a little bit easier? Because sometimes it's easier to count the opposite thing from what you're looking for than it is to count what you are looking for. Does that make sense? So complements can sometimes help you calculate probabilities. Next one is going to be a sample space. And we're going to do 4 children. So let's say answer the first question. The first question is, how many different things can happen when you have 4 children, right? First child, second child, third child, fourth child. 2 things can happen each child. 2, 4, 8, 16. That means that my sample space is going to have 16 things in it. So I know when I've got 16, I finish. Now I have to figure a way of writing them down. Once I've finished this table, I'm going to nip over and show you what this question looks like. Right. So you got to start somewhere. 4 children. What might be a good starting point so I can systematically write all of them down?
All girls.
Okay, let's do it as all girls. Would you agree that there's only one way that all of them are girls, right? That's the way. Okay, so where should I move to next now? Since I've got 4 girls, what would be kind of the next most obvious group to start counting?
One boy.
Okay, so you can have 1 boy with 3 girls, and the boy's last in the family, or he's the second last in the family, or he's the second in the family, or he was the firstborn. Do you see that that's systematic and it's easy to keep track of who you've done and not need to, double count somebody? Are we good? So far, so good. Right. So where are we off to next?
2 boys, 2 girls.
Right. So I'm going to start with 2 girls and 2 boys. Now this one's a bit trickier because there's actually 8 of them I happen to know, so I have to make sure I get them all. So do you know what I'm going to do to try and be systematic? I'm going to leave that boy at the end alone. And I'm just going to work out what happens to boy number, this boy here. Well, he could end up being the second one in the family. or he could go there. Now, all I've done there is keep the boy at the end. But the other boy, the second one, do you see how I've moved where he was born? Now I'm going to move the two boys along a bit. So I've now got this one. And I'm going to keep that one fixed. And then I've got that one done. Okay. Are we good with that one? Right. Who's the only? I said there are 8. There are actually 6. I made a mistake. Who's left?
One girl.
Oh, not yet. I've got one more of these left, and then we can do the one girls. What's this one? I've one more
Boy, girl,
combination.
girl, girl.
That's the one. Okay, one girl I heard. So how about a girl with 3 boys? Put it in second position. Put it in that position. Put it there, right? And then to finish with one, I have 4 boys. So 1, 5, 10, 16. Adds up to 16. Do you notice I got everybody? I think the beginning and the end are pretty easy. This middle one was the killer, wasn't it? That was the one that was hardest to keep track of people. But now that I've got those 16, we can answer lots and lots of weird, unusual questions. I'm going to show you what they look like in the homework. Right. You should all be looking at, hopefully, the homework. Right. What's the probability of getting a boy and a girl, 2 boys and 2 girls, 4 girls, 4 boys, all those kind of combinations? Do you see that those questions can now be answered by looking at my sample space? So for instance, what's the probability that you get 2 boys and 2 girls? Well, I know there's 16 things out here, and all of these ones here represent 2 boys and 2 girls, and there's 6 of those. So the answer becomes 3x. If I said to you, what's the probability that you get 1 boy? Well, I guess I should say exactly 1 boy. How many of those 16 events that you see in this sample space would end up being a family with exactly 1 boy and the rest girls? I think I heard it. 4. 1, 2, 3, 4. And the answer, obviously, simplifies. And you can even ask questions that are not so obvious. What's the probability that the last child was a boy? Well, if I look through this list and I want to find the last child as a boy, wouldn't that count? That'd be one of them.
8.
2, 3, 4, 5, 6, 7, 8. And then it kind of makes sense. Isn't the probability that your first child is a boy is a half, that your last child is a boy is a half, and your middle child, if you had a middle child of 3, wouldn't it still be a half? Doesn't really seem to change much. Are we comfortable about a sample space with 4 people in it, 4 children in this case, and how once you've created that, you can then answer these types of questions. We feel good about that. If there is any questions, now's your chance.
What about part E, like the sum of the answers?
Oh, well, if you add up, well, can you imagine they went and said, what's the chances that you get 4 girls? And then they said 3 girls. And then they said 2 girls. And then they said 1 girl. And is there anything I missed here? Oh, and 4 boys. That's slightly out of order. Well, when you add all of them together, do you know the answer becomes 1? Because isn't that basically everything that could happen being added together? So that's what they mean. So if you get all the probabilities to the earlier questions, if you add them all up in that particular story at least, that covers everything, and therefore you're going to get an answer of 1. Okay.
What about when you get the problem at the end of it where it says, what's the sum of your answers in parts B? Is it B minus D or B through D?
Yeah, B through D.
So that's just 1, right?
Yeah.
Like you add together.
You add them all up.
Okay, I just want to make sure.
Yeah. Unless some, I mean, I can imagine a different question where the first answer's a half, the second's a quarter, and the last answer's an eighth. Well, if you added them up, you would get 7/8, right? So I guess just add up the ones that they mention, because I know that they randomize some of these. So the one I've got might have been 1, but the one you got is 3/8 when you add it all up, or whatever the answer ends up being.
And then my other question is, because I haven't actually had the patience yet to fill in the boy girl stuff, does it mark you wrong if you don't put that in? I don't see anything that says that it cares. It's more like
it does have a thing. Let me show you where it is, because you may have just overlooked it, because it doesn't look the normal way that homework questions look with a nice neat box. Do you see the thing in there that I'm clicking on? That's where you type in boy, comma, boy, girl, whatever, and you put a comma between them all when you're finished. So yes, if you don't have it, you'll notice that your score's not 100% because that was not filled in. Does that help? So I mean, it is there, even if it's not so obvious that it's there. What we're going to do now is look at what is called conditional probability. And that's really how probabilities can change if you're given a piece of information. Now, I said could change because sometimes the information doesn't help. So let's do cards. Do we need to go through what's in cards, or can we assume that we all are happy with 52 cards and how they're made up? Do I need to spend some time just reminding you what's in a 52 card deck? Or are we good? We good? Do you all know what's in a deck of cards? Okay. So suppose I said to you, what's the probability excuse that you get a heart? So you pick one card from a deck of cards and you get a heart. There are 52 cards in a normal deck. We're not having jokers. And if you look at the ones that are hearts, 13 of them are hearts. Do you remember the hearts? There's 13 hearts. There's 13 diamonds. There are 13 spades. And there are 13 clubs. And these two are black in color. And these two are red in color. Now, that guy can simplify, and it simplifies down to 1/4. So you've got like a 1 in 4 chance that if you shuffle a card and you turn the top one over, hey, it's a heart. You've got a 1 in 4 chance that's going to happen. Now, a conditional probability would be written like this. And you would read this out loud as the probability that you get a heart given that you know it's a red card. Now, when you do conditional probabilities, you very often change the chance that something's going to happen. If I know nothing at all, there's a 1 in 4 chance it's a heart. Suppose I know it's a red card. Do you think my chances of getting a heart have now improved? Would that seem reasonable? Great. So how do we find this new conditional probability? The bottom number is not 52 anymore. The bottom number is this guy. And there are 26 red cards. And the top number is how many of those red cards are hearts. And isn't there 13 of them are hearts? So the probability that you get a heart, given that it's a red card, simplifies down to a 50-50 chance. Does that make sense that if it's a red card, it can only be hearts or diamonds, so you have a 50-50 chance that you get a heart, right? 1/2. What's the probability that you get a heart given that it was a black card? Now, this is a silly answer, but it's important that we understand how we do this. There are 26 black cards. Of those 26 black cards, how many, if any, of them are hearts?
0.
So the probability of that happening is a big fat 0. Do you see that you can tell people information that helps the probability, makes it more likely? But can you also be told information that makes it impossible for the thing you want to happen, right? That could be the case as well. So there's some examples. How about another conditional one with cards? Let's do an unconditional one, right? Just a straightforward one. The probability that you pick a card at random and it's a king. There are 52 cards in a deck. There are 4 kings. The answer simplifies down to 1 out of 13. Right, what do you think your chances of getting a king are if I tell you that it's a red card, right? So you know it's a red card. What's the chances of getting a king? Better, worse, or no different?
So it's 2 out of
Red 2, red
26.
Yeah, you're right. I heard parts of the answer. So would you agree that there are 26 red cards, right? So you know that's happened. Of those red cards, how many are kings? Be careful.
2.
2.
And doesn't that simplify down to 113? So can you see that this conditional probability, being told that it was a red card, had no effect on the answer, right? It's still 113. Ah,
Let's go on and draw other things with nice and white and the other proofs.
Okay, cool.
suppose we make it a little bit, not too much, but just a little bit. Oh God, I'm having a fight with Zoom right now. It's not wanting to close one of my windows. There we go. Suppose, where am I going with this? Oh, darn it, Spice, I don't know where I am. Here we go. just in case you do not know what a face card is, because not everybody plays cards. A face card is a jack, a queen, or a king. They're called face cards because if you ever look at them, there's a guy's or a woman's face on them. Now, each of the 4 suits has a face card. So if you put that together, there are 12 face cards. We're comfortable with that, right? Just so we know what the game is. Now we are going to do a conditional probability using face cards. So what's the probability that you get a king given that it was a face card? So in this story, you'd say, well, you tell me it's a face card, so I know it's one of these 12. Now, how many of the face cards are kings? Right? And that is a third. Now, if you compare that against the probability of just getting a king, which we've done earlier, can you see that if you know it's a face card, isn't the chances of getting a king increased quite a bit, right? It's much more likely, right? 1 in 3 chance from that. And here's some that sometimes throws people. You would think by symmetry, and you'd be wrong, but I can understand why you would think that if you switch the information around, that you probably should just get the same answer. No, the probability of A given B should be the same number as B given A, right? They're 2 sides of the same coin. That's what I would think would happen. But no, it doesn't. Since it's a king, right? You know it's a king. There are 4 of them. And this is the silly question. How many of those 4 kings are face cards?
All of them.
All of them. Can you see then that although these 2 probabilities are conditional probabilities, if you switch places, isn't the answers quite different? Are we good? Conditional probabilities. So an example of this type of question, just so we can refer back to what homework would look like. In question 7, they say, what's the probability that you get a face card given that it was a queen? Wouldn't that be pretty much the same kind of answer as this one, right? You're told that it's a queen, so there's 4. How many of those queens are face card? All of them are. The answer's 1. So there's an example of that happening. Question 8. What's the probability that you get a diamond given that it's not a club? Oh God, it's one of these. You got to be careful what not means, right? If you're not a club, doesn't that mean you're a spades, hearts, or diamonds? Right? If you're not a club, you're a spades, heart, and diamonds. So there's 39 of those. And how many of that 39 are diamonds? 13 of them are. So that answer is a third. You okay with that? Not a club, meaning 39 other cards. The nots always get me because sometimes they say not this and then not that, and then 2 nots together make a, yeah, I'm not doing my homework means I am doing my homework, you know, that kind of thing. So the English language can throw us a little bit. Oh God, I have to do this one only because of how silly it is.
So can I ask a question?
Sure.
I don't understand why you write 39. Where
Oh, here, right. So the information we're given is that it was not a club.
All of them. Okay. Okay.
So that
The
means
way of exclusion. Okay.
yeah. So that means it's a heart,
Mm-hmm.
a diamond,
No, I
or a
understand.
spade. And I'm just finishing this anyway since we started. Can you see where the 39 come from?
Way of
That's
the
what-
confusion.
Okay, right. This is a downright stupid question, but it is the homework, so let's do it. I don't even need to do any work for this. What's the probability that you get a club given that it was a club? And do not overthink this one. Uh-oh, some of you are overthinking it. If I tell you it's a club, right, I already know it's a club. What's the probability it's going to be a club? I don't want to write it. I'd rather somebody say it than I write it.
Isn't it 1/13?
No,
No.
you are
13,
overthinking it.
13,
So one,
Yes, which is 1.
13, 15.
13 13ths, which is 1. And if somebody said 1/13th, then that's what I thought I heard then. That's why I said no. It's 1. Are we good with the club probabilities now? We done enough of these? Okay,
can I ask a question, please?
sure. What you got?
Last homework, there were some questions about cards, and there was a combination, for example, king or another name of card,
Okay,
and king and another name of card.
right.
Thank you.
Let's do that then. Suppose I went and said, what's the probability you get a king or a red card? And what's the probability that you get a king and a red card? Now, in statistics and probability, whenever you see these two words, they have a very specific meaning. So, when they say king and a red, I want you to think of that as meaning it's both of those. So, that would be, what's the probability that you pick a red king? Well, I know there's 52 cards in a deck, but how many of those are red kings?
There are 2 red kings.
So the answer is 1/26. Now, when you see the word or, I want you to think of that as one and or the other. There's like an and that is implied there. So what does that tell me? Right, there are 52 cards in a deck. There are 4 kings. There are 26 red cards. And then before you finish, you might think, hey, 30 out of 52 make it look simple. That's not the case. Because very often in these or questions, you do what I call double dipping. You are counting the same card twice. Can you see that there are 4 kings and there are 26 reds? But haven't I counted some cards twice here? Haven't I counted red kings twice?
Because it's not specified which one named a king or which one red, right?
Yeah, so what you need to do here is 4 kings, 26 red, and then take away the both. Or you can say 4 kings and the 24 red cards that are left that are not kings. I guess you could say the same thing. The net effect is that when you do that particular question, you get that guy, which simplifies down to 7/30. So that is an and or difference. And is basically both things happening. That's typically a very small number. The or is one of them and or the other. And when you do those, be on the lookout for double dipping. Doesn't always happen. You know, if I went and said to you, what's the probability? Well, write it down. Suppose I said, what's the probability you get a king or a queen? Would you agree in this case, it's 4 add 4, and the answer is 8 out of 52, which cancels down to 2/13. And the reason for that is there's no overlap. Would you agree kings are kings and queens are queens? You can't, if you're counting them, you're not counting either of them double, right? You're not counting them twice.
I have a question.
Yes.
So I have a question on mine where it says probability of heart and out of a heart. And I did one as well, just like the club out of club. And
Right.
it says it's wrong.
So did it look like this as I'm writing it?
Yeah,
The answer is 1.
it says it's wrong.
Does it want a percentage, in which case you'll have to call it 100% then?
It says enter as a fraction.
Try 1/1 if it's been really pain in the butt. Try 13/13. But the answer is 1.
Can I ask a question, please?
If you just, Nadia, just for a few seconds, Taryn, any of those combinations, is it happy with?
So 13/13, it says no.
Right?
You do 100%.
You haven't done 1/1 or just 1?
I did.
And did it take it?
Nope.
Okay, I hold your question, Nadia. You are definitely next. I want to make sure that this is taken care of. I'm going to go in and do that homework question. For me, it's question 11.
Yeah, it's
So-
11 for me too.
Right, so it's going to take us a few seconds just to set it up as a student, so I can type it in, you know, in the same way that you would do it, and so we can check. Is it
I'm gonna need a
work or not?
reset because now I have no more options.
I shouldn't have gave you too many options to do. That was my fault. Okay, so I'll go 107. We'll do. What do I do? I do students view. I'm almost there, everyone. Okay, I'll move this over here. I'll do simple probabilities. And it was question 11. Okay, so I'm going to go in and show you what I'm looking at. You can see if you get the same result. Okay, so 2 cards are drawn from a standard card, and one of the 2 cards is noticed and removed. Oh no, this is not the same question. This is a 2-card question, because you take it and then you remove it, and that is not the same.
Oh, wow. Okay. That must be why I
Right.
was getting these wrong.
Yes. We haven't done those ones. I should have looked at is that we've done the single ones, which is question 9. So I guess now it's time to do the double ones. So before I do that, we do have a question that she'd been waiting very patiently for. So Nadia, what was your question?
My
If a
question,
single card, by the way, that is still correct, but that's a single card story, right? We're going to do a double card story in a minute. Right, what you got, Nadia?
so my question is the first one on a top line, probability king or red. Why did you write -2 on the top?
Oh, okay.
I mean 4 plus 26 and
Right.
-2.
4, that's the kings, plus 26, that's the red.
Mm-hmm.
Take away 2, and 2
Why?
is for the both red kings. I've already counted the kings, and I've already counted the reds, but inside the red, aren't they 2 red kings? So I can't count them again because it's the same card and I'm counting it like in 2 different places. So
Oh.
the takeaway 2 is to account for the both.
Oh, okay.
So if you wanted to see what that would look like in a formula, it would look something like this. It would be the number of kings plus the number of reds, take away the number that are both out of 52. So when you do an OR question, it's typically how many in the first group plus how many in the second group, take away whatever number happens to be in both.
Okay.
Well, now we're going to look at two card stories. Now, there are two versions of these, so that's another thing that we have to be careful about. In one of them, it's with replacement. And the other is without replacement. Now, what we're talking about here is two cards, right? So you shuffle the decks and you take a card and you put it down. So let's do the with replacement version. So what happens here is you take the first card, you look at it, and then you put it back in the deck. Now, in those stories, which are kind of artificial, I don't think many people play cards this way. You know, oh, I got an ace, and then you put it back in and you shuffle and you see if you got another ace. But it could happen. So if you see the word with replacement, it means you put it back in the deck. Let's look at the probability that you get an ace and then another ace. Okay. In these situations, it's the probability that the first card is an ace, and then you multiply it by the probability that the second card is an ace. So we're doing two events like this, right? In a normal deck of cards, when you take the first card out the deck, isn't the chance of it being an ace 4 out of 52? Right, there are 4 aces out of 52 cards. Now, if you take the first card and you put it back in the deck, what's the probability that the second card is going to be an ace? It's the same number, isn't it? It's still 4. Now, that is an ugly, ugly brute of a question. So I would let the calculator do it for me. So here
Mr.
goes.
Robertson,
Yes.
so when it says put it back on the deck and then it says probability of the second ace, is it this? Could it be the same ace?
Yeah.
All right.
You could get an ace of diamonds and then, oh God, would you believe it? The same ace came out the second time.
Same one.
Because if you did it with, but it doesn't need to be the same ace. Couldn't it be an ace of diamonds and then an ace of clubs? It still counts as 2 aces. You see what I'm saying?
Right. Okay.
Right.
Yeah.
Okay. So horrible fraction. I'm going to put brackets around it just to be safe. 4 divided by 52 times another 4 divided by 52. This might be too much for the calculator, in which case I'll have to do a backup plan. Yeah. Looks like it's going to be too much. Whoa, I take it back. It made it. It's a 1 out of 169. So that's with replacement. When you do replacement, do you see how the probabilities don't care what the other guy was, right? You're basically starting from scratch each time. Now, if we do without replacement, which is probably more realistic, you take your first card, you look at it, and you keep it on the table. And then you pick your next card. So let's see what the probability of getting 2 aces is now. Well, it's a probability that the first card is an ace, and it's going to be multiplied by the probability that the second card is an ace. But there is going to be a difference. The first card, 4 out of 52. Fine. Now, you've shuffled the card. The first card is an ace. It's on the deck, right? It's on the table. And it stays on the table. So how many cards have you now got in your hand? You've got one less, haven't you? Of those 51 cards, how many of those 51 are aces? Because that's the chance that the second card is going to be an ace.
3.
3. And that's the ugly guy that we're now going to put into the calculator. So brackets 4 divided by 52 times brackets 3 divided by 51. Horrible answer. Math, number 1, go for it. It's 1 out of 221. Why is it harder to get 2 aces when you don't put the ace back in the deck? Does it make sense that it's harder to get that than it is when you put it back in? You see the odds are a little bit smaller, right? Harder to help. Now, let's do the club, given that it was a club story. Right, now in the club story, was it with replacement or without replacement? Try to find the story here. Single card, single card, single card. It's question 11. Okay. 2 cards are drawn. One of them is noted and it's removed, so it's removed. Find the probability that the second card is going to be a spade. Then there are only 51 cards now, right? The first card has happened. And would you agree that in this case, clubs, I should say, one of them has been used up. So it's 12 out of 51. So this is a conditional probability. What's the probability that your second card is a club, given that your first card was a club? Now, since you know that the first card was a club, that means that you're only going to be 51 cards and only 12 of them are clubs. So that's what the answer should be. Taryn, you just shoot me an email sometime and I'll give you some more shots to type that one in. Okay. Let's do another one. This is question 12. 2 cards from a deck and it's removed again. And this time is, what's the probability that you get a red card given that the first one was black? So that means there's 51 cards left, right? Because the first card is a black and it's happened. Of those 51 cards, how many of them are red?
Is it 25?
Did a red get used up?
Oh no, 26. 26.
Yes, 26. Here's a similar looking one. What's the probability that it's red given that the first card was red? Right, there are 51 cards. The first card is red, you've left it alone. What's the chance that your next card, right, it's basically your second card, is also going to be a red?
So is that one? 27?
Right.
That
So
one's
51, right, cards left. How many of those are red cards given that the first card was itself was red?
25.
25.
Yeah.
25.
And there you go. Are we good with the 2 card ones, or you want to see some more 2 card stories?
Mhm.
Can I ask a question, please?
Yes, what you got?
Why do you write down beneath 51?
The reason why there's only 51 is that you were told that the first card was a red card and it was kept on the deck. So that means it was used up. So when you come to taking the second card, you've only got 51 cards left to play with and 25 of them are red. So can you imagine this was my deck of cards?
Mhm.
and the first card came out and it happened to be a red card,
Oh, okay.
and I left it on the deck. Can you see that my new situation
Okay.
only has 51 cards in it? And so what I'm looking at here is, out of those 51 cards, how many of them are red? And the answer is there's only 25 of them red, because one of the other reds has already been eaten up here. So that was the logic of how that works.
Okay. Thank you.
Okay, 25. Going to look at die stories now, dice stories. When you roll a dice, there are only 6 numbers, and there they are, right? So that's essentially my sample space. So if there's one dice and someone says to you, what's the probability that you get the number 5? That's a single probability. It's 1 out of 6. If I said to you, what's the probability that you roll an even number? 1, 2, 3. There are 3 of those. And that would be just an unconditional probability, right? Just count how many out of the 6 happen to be whatever it is you're interested in. But then you can have conditional probabilities. So for instance, what's the probability that you get a 5 given that you're told that that was an even number? Well, since I know it's an even number, it's a 2, 4, or a 6, so there's 3 then. Of those 3 even numbers, would you agree none of them are a 5? So the answer is 0. On the other hand, what about the probability that you get a 4, given that it's an even number? Well, there are 3 even numbers, so that goes in the bottom. And then how many of those even numbers is a 4? And the answer is just one of them. It's a bit like the card, doesn't it? What's the probability you get a club given it's black? What's the probability you get a king given it's a face card, right? Single, one event, one roll of the dice, some conditional probabilities concerning it. That's basically what question 13 was about. Actually, that's what 14 is about as well. Are we okay with a single roll of the dice calculating probabilities? Is there any questions you want me to talk about there? Now we're going to move on to 2 dice. But in particular, the sum of the 2. So here's something I prepared earlier. There are 36 ways in combinations of 2 dice being rolled. Here they are, all here. Look like coordinates. For instance, that would be a double 6. That would be a 5 and then a 4, right? One was a 5, the other was a 4. So if I said to you, what's the probability that you get a sum, right? And the sum is 5. Well, the bottom number is 36. And then you look for totals or sums of 5. That one, that one, that one, and that one. So that would be simplified down to 1/9. Now let's do a conditional probability. What's the probability that you get a 3 given that the sum was a 5. So what we're telling it is that the 2 dice add up to 5. And what's the probability that you have a 3 there, right? Now, if you look at my little table here, maybe I should just write them down. These are all the ways in which you could get a 5. Right? That's it. Those give you the 4 that goes in the bottom. What's the probability that there's a 3 in one of these dice? Can you see it's happening in 2 different locations? And that means that the top number is 2. And so you've got a half. So when you do a conditional probability like these, this expression becomes your new sample space. This is what goes in the bottom. And then only using whatever this is, in this case there's 4 situations, you can then answer getting a 3. What's the probability that you get a 3 given that the sum is odd? Wow. You have to go to these 36 guys and you have to count how many of them would end up giving you a sum that's an odd total. Well, that one adds up to 2, so that's no good. These 2 work because they add up to 3. So there's 2 of them. 1, 2, 3, 4 of them. 1, 2, 3, 4, 5, 6 of them. 1, 2, 3, 4 of them. And 2 of them. So that's 10, 4, 8, 10, 12, 14, 16, 18. After all that hard work, there are 18 different things in that table that have a sum that's odd. Of those 18, and only those 18, how many of them have a 3 in them? Well, none of them. That one and that one, so that's 2. That one's 3, 4, 5, 6, 7. That was it. I only counted 7. Hopefully I didn't miss any. So whatever goes here is your new world. In this case, it's only guys from that table that add up to an odd amount. There's 18. And only look at those 18 to see how many of them had a 3 in them. And 7 out of those 18 pairs had a 3 of them. And that's the answer. I don't think
Can I
I'm
ask for
seeing.
an example?
Say again, Torin?
Can I ask for an example?
And
I
what, another?
tried. Yeah, I went ahead and did most of this already, but one problem really confused me.
Sure, give me it.
So odd given that a 5 was rolled.
So the probability that the sum of the total is odd given a 5 was rolled, right?
Well, it just says odd. Was it supposed to be total? Oh yeah,
I
guess
would
you're right.
I would assume
Yeah.
that they are totals
Given
just
the
because
5
of
was
the
rolled.
story.
Yeah.
Right? Right. So if I go and I know the totals are odd, I'm writing them down here because it's probably easier than just pointing with my fingers. So here are the guys whose totals add up to an odd amount.
Oh, I think what I did is I just looked at every single 5 that like things that could be a 5, and I made my
But not all of
sample
them
size
count.
11.
You know, like
But
a double
yeah,
5
I
doesn't count.
reversed it.
Does that make sense?
Yeah, that makes sense.
Okay.
So be careful of that. Don't flip them.
Right. Well, since I've already kind of, started, so I guess I'll finish. So what we got? We got 6, 3, 5, 4, 4, 5. Finally, so 3, 6. Yeah, that's adding up to 9. If we go on to the 11s, then where's the 11s? That's the 9s. 11s. There's a 6, 5, and there's 5, 6. So there's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So there are 18 things in this list. Now, how many of them? I just did this question the wrong way around. I've just answered the probability that you get a 5 given that the total was odd. Right, that's given the total was
Okay,
odd.
that's what I was so confused.
So 5 is, well, let's answer this question. There's 1 there, there's 1 there, there's 1 there, there's 1 there, and there are 2 more there. So I believe that's 6, which ends up being that. Now, if you switch places on them, so the total was odd, given that you got a 5, right? I won't write them down this time because it would take me forever in a day, but can you see that's got a 5? That's got a 5. In fact, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, don't count that one, 11. There are 11 combinations out there with a 5 in them, right? And how many of them gave you an odd total? That one didn't count, this one does. That one adds up to 8, so it doesn't count. This one does. That one adds up to 10, this was 11, so that's 3, 4, 5, 6. 6 out of that 11 added up to an odd total. So if you went through this and you picked,
I only
that
found
row-
5. What did I miss?
well, maybe what, you have 5 there instead of 6? Let me double check then. I don't want to mark these because I'll never get the thing off. That one counts, it's got 5, right? So is it a total? No, doesn't count. That one counts. 1, don't count it. 2, don't count it. 3, okay? 4, don't count it. 5, don't count it. 6, I make it 6.
Oh, okay, I see. Thank you.
Okay, we are fighting our way through these. And I don't know, do you want me to do some more double dice combinations? Have we seen enough of these guys? Any questions? Or shall we move on?
It says that's wrong.
Because I can't count.
I don't know. I did 5 over 11 and I just did 6 over 11 and they said both were wrong.
Well, let me check. What question are you doing? Because I might not be doing it might not be your question. I have
I'm
to make
doing-
sure, because it could be one of those, and the first one was that again. So tell me your question number, sorry.
It's 15 part B.
Okay. In my 15 part B, suppose a pair of dice is rolled. Consider the sum of the numbers on the top of the dice and find the probabilities and enter them as fractions. Okay. So odd, given that a 3 was rolled, and you got given that a 5 was rolled.
Yeah.
The only way I could have counted that wrongly is if the double 5 doesn't get counted, but they should have been clear about that.
Well, I did both of them and they both said it was wrong.
Yes, but if you don't count the 5s, you get 6 out of 10, which is 3/5.
Oh, okay, yeah.
Because have you tried that?
Let me see.
I've tried 3/5 and it said it was wrong.
Oh, we are having fun with this one, aren't we? I know what I can do. I can cheat and find out what the answer is and then scratch my head profusely when it doesn't make sense. Sometimes WebAssign just does things, or I don't know what it does, but it does things to confuse the heck out of me.
Professor,
What if
Yes.
I change to a double if 5 was wrong? Is it 1/11?
Well, no. Let's find out. I'm just opening this one up and I'm going to put the answers in. At least I'll get the answer to whatever version it has. What number was that again?
15.
A double.
Oh,
I have odd given that a 7 was rolled. And the answer is 1. Oh. I think that when they say given a 7 was rolled, they must mean given that the sum was 7, not
Oh.
the number 7. Right, I'll show you what I'm looking at here. For the sake of one extra word, it would make so much more sense to me. Right. This is a version because they changed the number. So what's the probability that the sum is odd given a 7 was rolled? Now, you can't get a 7 if it was a single dice story. So that must mean that the sum was 7. And so what they're saying is, what's the probability that your total was odd given that your total was 7? And the answer is 1, because it's guaranteed, isn't it? So that's what the buggers are doing, if you pardon the French. When they want a single dice, they'll phrase it like that. If they just say a number, they mean the total. Not good. That is I blame their question, not the answer, right? Because if you interpreted it the way I interpret it, my answer there is totally correct. Because I'm thinking, given that a dice was a 5, what they're really saying is given the total was a 5.
can I have a reset?
Yes, you will do that. You will get another reset. Keep it to number 4 the next time so that we can have one last shot at it before I pull my hair out and complain profusely. They just should be careful. You know, when I do questions for your midterm, there will be a lot more words so that you won't get that confusion, right? So if I did a question like that, it would be, what's the probability that you get a total of 5 given that one of the dice was a 3, right? I'd phrase it in a very clear way so you know what you are and what you're not counting. And that question there was not really nice because they could have phrased it a lot clearer. So it's not as hard as they're making it out to be. We've got time. We've got to get moving. Okay, I want to show you, and there's more of these dice ones coming, but I want to show you a tree diagram. And in this story, what you're going to do is 2 or maybe sometimes even 3 people being chosen. Let's do a 2-choice story. So I'm going to imagine that we had 20 students. And you don't know this because I'm making it up, that 5 of them were Scottish and 15 of them were English. So we're in Britain and there are 20 students in this class and 5 are Scottish and 15 are English. And in this 2-choice story thing, you're going to pick 2 people from the class without replacement. In other words, when I pick somebody, they're used up. And we are going to create a tree diagram to try and show what that would look like. So there's a Scot and there's an English. So this is the first person that I pick. 5 out of 20 are Scottish. and 15 out of 20 are English. And on these little roads, these little pathways, you put the probability. So when I look at that, I can say, 5/20th chance of picking a Scotsman, 15/20th chance of picking an Englishman. And then you do your second person. And that second person could be Scottish, or they could be English. Could be Scottish, or they could be English. Now let's see what these probabilities look like. The first person that I picked out of the class was a Scotsman. That means there's only 19 people left for my second choice. Are you happy about where that 19 is coming from? It's a bit like using up one of the cards from a card of deck, right? There were 20, I've picked somebody, he was a Scotsman. That means there's 19 people left. What's the chance that the second person is a Scotsman? Well, how many out of that 19 are Scottish, based on what happened here?
4.
Agreed. And wouldn't the other 15 be English? Now look at this one. It was an English person that we chose. There's still 19 people left. But the chance that the second person is Scottish, well, there's 5 out of the 19 that are Scottish, and there's only 14 out of the 19 that's English. And we call these tree diagrams. They look like trees, you know, if you stick them that way around. Now, what you then have to do, and I'm changing color here, is that you then find these end probabilities. So if I wanted to know a Scotsman was first choice, and then I got lucky again and I picked another Scots person, the probability that that combined effect happened is what you get when you multiply these together. And I'll let the calculator do that for me. Oh, I already know the answer, it's 1/19. Now you want to do this pathway. Scotsman followed by an Englishman. Well, you multiply the Scots one times the English one. And here we go. Put a bracket around it. 5/20ths times 15/19ths. And then do the old math button and hopefully get a fraction out of it. And we get 15 out of 76. Now, what about an Englishman first and then you chose a Scotsman? Well, you multiply those two probabilities together. You get that. And then lastly, an Englishman first and still another Englishman after that. And you multiply their probabilities together. And I'll put that fella, 15/20ths times 14/19ths, and the math button with 1, and I get 21/38ths. So what I've done here is I've completed our first tree diagram. And these are the important guys. These end probabilities are very useful. It's not too obvious because these are really ugly looking fractions. But what should these 4 answers always add up to if you did it correctly? It's the same number every time. What would you expect all 4 to add up to?
One.
Yes. Does that make sense? Aren't these the 4 eventual everything that could happen is encompassed in these four. And if everything that could happen is encompassed, then their probabilities will be 1. Why is that useful? Well, you know, if you're doing a really messy one and you've got time, shouldn't you just add the 4 answers together on your calculator and see if it's 1? And if it's 3/4, you've missed something, right? And if it's 15/9, you've got something too big, right? It's just a very quick check. Now, once you've created this fella, you can answer any question you could almost imagine. So here's some examples of what I could get from this table or from the green guys at the end. For instance, what's the probability that the first person was Scottish? In other words, the first person I chose was a Scotsman. Now there's the answer right there. It's in my tree. What's the probability that the first person was Scottish and that the second person was also Scottish? Well, wouldn't that be this guy at the end? First. So in this case, you just did that one and stopped, right? In this case, you went this one and got that one. What's the probability then that the second person was Scottish? Now, that guy there is the second person being Scottish. And isn't this one here also the second person being Scottish? Right, so what's the probability then? It's this one plus that one. So it's 1/19 plus 15/76. That's why we have calculators. It's a quarter. Are we good so far? Are you happy about how you construct one of these from the story that you're given and how I calculated these? This is your chance to tell me, and I'll see if I can work on it. Okay. From this guy, you can then create a table like this. Okay. First person is Scottish, second person is Scottish, right? Probability of that happening, 1/19. First person Scottish, first person Scottish, second person English, ends up being for Scottish. English ends up going here. English followed by Scottish is that one, and English followed by English is that one. And basically, any combination of those four will probably answer most of the questions that you're looking for. I'm just putting them into a little table, which is just a different way of organizing this information here. And that's the end of this tree diagram. And that is the end of, believe it or not, simple probabilities. So what's left? complex probabilities. How complicated can these guys get, I guess, is the question. I'm just setting up the next group of questions. And that's what we're going to be covered for the midterm. Takes a few minutes to load up the next section. Right, there's 10 questions in the last section, the complex probability ones. And I'm not good at multitasking. When I do multitasking, I end up pausing a lot because I can either talk or do, but not both. Here we go. Right, hopefully you're looking at 13.4, calculating complex probabilities. Okay, now, suppose you roll a dice is rolled twice, and let A, the first toss is a prime number, and B, the second toss is a 3. Are A and B independent? Right. Now, what does independent mean as far as probability is concerned? It means that the probability of one event has no effect on the probability of the other. So, write this down. A and B are independent if probability of A given B is the same thing as just the probability of A. Okay. So, jumping around a little bit, but let's show you how that works. Suppose A is getting, this is from a dice, right? A is getting a prime number, and B is you get a 3. Okay. Do we all remember prime numbers are just numbers, not including 1, you don't use 1, that you can't divide by anything except themselves and 1. So prime numbers would be the 2, a 3, and a 5. Those are the prime numbers. So if I said to you, what's the probability that you get a prime number given that it was a 3? Well, since it was a 3, there's only one number. What's the probability that this guy is a prime number given that it was a 3? And the answer is 1. What's the probability that you get a prime number? Just a normal one with no extra information. And the answer is 3 out of 6 is a half. Do you see that these two are not equal to each other? If they are equal, they are said to be independent. If they are not equal, then we say they are dependent. So what that means is that the outcome of A has an influence on B, right? They're connected in some way. That one was a bit silly because one of the answers was 1. So let me try a different tack on this. Let's A be a red card and B be a king. And we're going to test are they independent or not. So what I'm going to do is I'm going to find the probability of event A, which is the probability that you get a red card. Well, that's simply just 26 out of 52. That's going to happen about half of the time. Now I'm going to find what's the probability that I get a red card given that it's a king. Well, there are 4 kings. Of those 4 kings, how many are red? There's a king of diamonds and a king of hearts, so 2. Wait a minute, isn't that answer the same? So that means red cards and kings are independent events, right? If you know it's a red card or you don't, if you know it's a king or it's not, one event has no influence on the chances of the other event happening, right? They don't interact. Even although there are red kings there, that doesn't matter. Probability independence just means that they don't affect each other. In other words, this conditional probability is the same answer as it would have been without it. Right? Would it have mattered if I'd switched places? And I called this A and that B. Would it matter as far as the conclusion is concerned? No. If 2 events are independent, it really doesn't matter which one you decide to call A and which one you decide to call B. If they're independent, the 2 answers will be the same. Now, if I switch places, the 2 answers might be a quarter and a quarter, or 1/13 and 1/13, right? They'll just be the same. They may not be the same as a half, but they will be the same as each other. Are we good? Independence, little side issue. Right. Going to do basically tree diagrams. That's what most of this last part is about. So let's have a situation where it could be A, it could be B, and it could be C. And this happens, this happens a half of the time. This happens a quarter of the time. This happens a quarter of the time. And A could be a guy called D or not D. So it could be yes and no. Yes, no, yes, and no. And let's say that this is a 0.5. That's weird. Okay, 0.5, I'm only copying what they've got. 0.1, 0.9, 0.7, 0.3. Right. Straight off the bat, either make everybody fractions or make everybody decimals. Would you agree mixing and matching isn't really a good idea? So I'm going to replace this by 0.5, this guy by 0.25, and this guy by 0.25. Now, if I went and said to you, what's the probability you get an A and then you get a D? Then it's this pathway here. See the one? And that would be 0.5 times a 0.5. And that answer would be 0.25. If I said to you, what's the probability of a C followed by the complement of D? It would be a 0.25 times a 0.3 0.25 times 0.3 0.075. And then you might get a guy that looks like this. What's the probability that you get the complement of D given that A is harmed? Now, you know A is harmed, and they're asking you for this guy. So the probability that D, the complement of D harms given A. Do another one like that. What's the probability of B given that it's D harm, right? Oops, wrong way around. probability of D hat given B. D hat given B, 0.9. This section is relatively quick for the first few. So let me jump right in here and show you question 3. Which path number represents this guy? So D hat given that A1 is harmed. D hat given A1 is harmed. You can see that's path D. Oh, there's the answer too. They wanted to know what the probability is. It would be D hat given A1, D hat would be 0.4. Oh, now find this guy. Somewhere in this T diagram, there's a pathway that represents this guy. So the way I tend to read these is A1 first, which is this one, followed by that guy, which is this one. So it's going to be this fella and then this fella. So if you multiply that guy by that guy, oh, there you go, you get 0.2. So what you're looking for is the half multiplied by the 0.4, and that's where the 0.2 came from. Okay, here's another one. Told you these are going to be quick. This combination of this pathway times this pathway ends up being one of these guys here. What path number, just tell me 1 to 7, would be this guy? Look for a pathway that goes to B2, and then from B2 it goes to C1. I know it's like reading backwards, but that's the way these work.
3. Is it 3?
Let's see if she's right. Would you agree that's B2 and then later on C1? Pathway 3, yes? So if you wanted to know what the answer was, because they want a number, don't you multiply this piece, 1/4, by this one? See the pathway that we followed? Multiply the roads, 1/4 times 1/4, 1/16. Darn it, we're almost finished. Okay. The last couple of questions, I'm going to have to create a tree diagram and then we can answer the questions. So hopefully you can hang in there for just a little while longer. In this story from question 6, a certain slot machine has 3 identical independent wheels, each with 13 symbols on it. And then they go and they describe what the symbols are made up of. And one of your screens has decided to get in the way, so I can't read it all. Okay, so there are 13 symbols. There's a bar, one of them. There's 2 lemons. There's 2 bells. 3 plums. 2 cherries. 2 oranges. Oh, I take it back. I do not need, thank goodness. I do not need to draw a tree diagram, because if I did, would you agree it would probably take up 5 pieces of paper? Because wouldn't the first one have to split like that? And then each one of them would have to split And then each one of them would have to split and you'd be forever drawing them. So how can I avoid that? Well, the good news is that these do not affect each other. In other words, if a bar comes up in the first row, couldn't a bar come up in the second row? It's not going to change. So what's the probability that you get 3 bars? You just find the probability of each one separately, and then you can just multiply them together. Now there's a 1 in 13 chance that it's a bar, and the second one also has a 1 in 13 chance, and the last one has a 1 in 13. These numbers don't change. In the previous one they did, but in these ones they don't. And there's a cool little thing you can do in a calculator. Have you ever seen the little power 3 symbol? So you don't have to keep writing the thing over and over again. Here we go. 1 divided by 13 raised to the power of 3. And as a decimal, 4.55 e to the negative 4 is 0.000, I'll round it off 5. Let's do the probability that you get 3 oranges. 1 orange, 2 oranges, 3 oranges. 3 out of 13 in each case. In this case, you multiply them together. 3 divided by 13 raised to the power of 3, and I get a number I can actually write down, 0.0123. You can even do things like, what's the probability that you get cherry on the first row? Well, that's just 2 out of 13. Because we don't care what happens, we're only interested in the first row. And if I do that one, 2 divided by 13, I get 0.154. So for these questions where you do not need to worry about things changing, I do not need to do a tree diagram. All I need to do is multiply the probabilities together. I mean, I could even do a funny one like this. What's the probability that I get a bar, then the orange, and then a cherry? That's the probability that you get a bar, multiplied by the probability that you get an orange, multiplied by the probability that you get a cherry. That wouldn't win me any money at all. 1/13 for a bar, 3/13 for an orange, and 2/13 for a cherry. Then I just multiply that whole horrible mess together. And I'm pretty sure I'm going to get one of those really weird scientific notation guys. Oh, I take it back. 0.027. So as long as nothing changes, in other words, you can get the same guy over and over again, they never get used up. Just multiply whatever the events are together. So if it's 3 oranges, you can go orange, orange, orange. If it's just one guy, you just have one answer. Any combination would work. Okay. 3:15. Am I going to get this all done? He mumbles to himself.
Could you remind me again of the date of the test?
The test will be a week today.
Will it be during class time?
Yes. And it will last
Okay.
3 hours. Okay, let's, okay, what have I got? Let's do a 6 coin one, which is essentially question 7. And I'll do one more after that, and then I can spend what time I've got left talking about your midterm. What's the chances that you throw 6 coins in the air and you get 6 tails? Okay, imagine that would be tails, 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 tails. Now, when you throw a coin in the air, would you agree that they're independent of each other? The fact that the first coin's a tail has no effect on the ones that come after it. That means I can just find the probability of each one separately and then just multiply them all together. And that is a half. And so is that one a half. And so is that one's a half. And so is the last one a half. And since there are 6 of them, can't I just write it like that to make my life easier? It's a half times a half, 6 different times. So on the calculator, 1/2 raised to the power of 6 ends up being that guy, which is 0.015625. Or if you want to see it as a fraction, 1/64. So if you went through 6 coins in the air, the chances that every single one of those guys was going to be a tail is that guy there. And so the last one I've got to talk about is the probability that, oh, so it's 5 coins now, I've changed the number. And what's the probability that you get at least 1 tail? We did at the start of today an at least question. And I said, look, when it's these kind of situations, it's sometimes easier to find the opposite of event, right? The complement. Now, the complement of at least 1 tail is none of them are tails. Now, that should be easier to do, because if you have 5 coins and none of them are tails, isn't that another way of just saying they were all heads? Right, so I'm looking for the probability at least 1 tail. Too hard to do. So I'm going to find its complement, the opposite of it, which is no tails. And no tails, when you do 5 coins, ends up being all these heads. Won't that be a half to the power of 5? A half times a half times a half. And that guy ends up being 1 out of 32. Of course, that's not the answer, but that's going to get me the answer. This guy and this guy are complements. I found out what this one is, so isn't he the rest? So I indirectly got the answer by finding its complement and then subtracting it from 1. Oh, that was a little bit of work for one day. Hopefully you have time to look it up. So what we got left now, it will be in a minute, is spend some time talking about your midterm. Here we go. Right, just to repeat what we already know about your midterm, is that it is going to be a week today, so that will make it, what, the 11th? And it will take place for 3 hours. So we'll start at 1, but we'll finish at 4. Obviously, if you finish early, it doesn't matter. You're finished. So let's, once this thing kicks in, let's talk about what your midterm is going to involve. Okay, I think I'm ready to show you. Right, here are your topics for your midterm. Basically everything we've done over the first 5 weeks. You will not get anything about WebAssign in your midterm. Your midterm will be on a PDF. So what will happen is, and we'll talk in more detail about this on Thursday, because I'll have it set up by then, is that there'll be a special module called midterm exam. And in that module, you'll have a link. And when you click on it, a PDF will open, and your test will be like it was written on paper. And you do all your answers on paper. And then you take a picture using your phone and you send it to me, convert it to PDF, and you send it to me by uploading it into Canvas. So I'll show you all that good stuff on Thursday. But here's the topics. All the financial stuff, which is chapter 11, and all the probability stuff that we just kind of finished today, although if we need some more time, I'll definitely go back to it on Thursday. Now, when you're doing the test, it's pretty much going to be in chronological order. And by that, I mean, the first question will be from interest, and the last question you'll see will probably be something to do with 5 coins and what's the probability that they're all heads, right? Something like that. The financial stuff, you will be given the formula that you need to use in that question. So you don't need to think, oh God, there's 8 formula, which one works for this story, right? That's not going to be a problem. You will be given the formula. It's your job to figure out where the numbers go and how to calculate them and how to interpret the answer and things like that. So that should make your life a little bit easier. There aren't really any formula in probabilities, but if you can't remember how many cards there are in a deck of cards or something, I would just write those things down, right? Just so that they're handy. You are allowed to have notes with you, so you might want to put some good notes together, especially things maybe on tree diagrams that you might find, you know, you're still getting your head around. But I wouldn't spend so much time on writing the formulas down, except you might want to do examples with numbers so that you can remind yourself how to do complicated financial questions on the calculator. If you remember how I did it, I broke them into little bits like 1, 2, and 3, and then I combined them. That might work for you, it might not. But somehow or other, you've got to figure out a way of coping with the fact that these are midterms. And there's your guys. Any questions?
I have a question, please.
Yes,
Are we
Nadja.
allowed to use a calculator?
Yes, you are allowed to use your calculator if that's what your question is. Any other questions?
How many questions are going to be on it?
I have no idea yet because I haven't written it, but I'll give you a kind of gut feeling. And they're going to be one on everything. So that's 3, 6, 7, 8, 9. But there's definitely going to be some which will double up. So somewhere in the region 10 to 15 right now. By the time Thursday comes round, I'll be able to narrow that down to within, you know, plus or minus 1. But remember, you've got 3 hours to do it. So it's, you shouldn't really have an issue with time. I try not to do my tests so that you're stuck. You know, you could do the last 2 questions, but you don't have time. Any other questions?
So you said that we are supposed to give it to make it during class, is it right?
Correct. So it's going to be from 1 till 4 on Monday. It's here somewhere. There we are. 1 to 4, Tuesday, I should say, is your midterm exam. Does anybody remember, it's in the syllabus, what percentage of your grade is midterm?
No.
30% of your grade. So you wanna, you know, it can certainly help your grade. So you don't want to do anything that's, I'm so easily distracted. Right, where was I? Yeah, you want to make sure that you focus on doing the best you can. 30% can kill you. It can also improve your grade a lot if you do well. So it works both ways. So focus, focus, focus. Okay.
Are we allowed to use our notes or not?
You are. You're allowed to use any physical notes that you've written down. So if you write down anything that you might have that was helpful to you, now it doesn't need, it can be anything. It really, notes are very flexible. People are different. I've seen some people who write cards where on the front they put a story and on the back the formula and the working. So that if they say, oh yeah, that one's a mortgage question. I have a question that looks just like that. I'm going to have a look at, yep, that's what I did. That number goes there, this number goes there. That's one way that people do it. You might do a tree diagram. I keep plugging this guy because it's a pretty important concept that you need to get around. You might have a little story written and a tree diagram, and not just that, little arrows and things like post-it notes saying, this is how I got that number, that's why it goes there, and this is how I got this number, and that's why that's now 14. It used to be 15, but now it's 14. You know, little aids to yourself so that when you construct one, you know what, you know how to do it and why things went where they did go. I tend to do my questions pretty much the same as the homework questions, but I will definitely make sure that I phrase them much better than some of the questions today were, so that if it is a total, I will use the word total. And if it's a single number, like a dice is 5 on it, I will say a single number with a 5 on it, right? So that we don't have to try and second guess what they're meaning when they write things down. You get partial credit, so make sure that you show all the working. Even if normally in homework you skip some lines, because you know if tons of questions and it's a lot of work to write them all down. Try and make an exception for the midterm of putting down all the numbers that you did, you know, like in the financial question, good example. You know, I have the formula, then you put the numbers in, and then some of you just have the answer. Maybe it would be a good idea to do the 1, 2, 3 here, so that if you screw up, I can say, ah, she did that bit, but she did those bits right. So if you get it 3/4 right, you're getting 3/4 of the points. The worst thing you can do in a, say, a finance question is, oh, I've done 20 of these, I could do this in my head. And all you write down is $14.30. Didn't bother telling me the formula, didn't bother putting the numbers in, didn't show any kind of work in. You just put the answer. And the reason why that is dangerous is, suppose it was $16.13. I get nothing to give you because there's nothing to say. So in a normal homework question, I understand, boom, 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 $14, right? 2 minutes, done. But try and be a little bit more convincing when you're working. Anything else?
I have a question, please.
Go for it.
So I have some problems with my phone. I just, my phone broke recently and I bought a new one, and I'm not able to upload any any applications. How can I handle
on your new phone?
Yeah, I have, but well, I didn't think about it. I just deleted some applications that were already in a phone, and after that I'm not able to upload new applications. So, and I didn't fix this problem. What can I do to send to you?
Beat up your sister, your daughter, your partner, steal their phone for the test, and use that phone to get it to me. That's option 1. Option 2 is, if you have a printer, you can use your printer to scan your working, and you could send it to me that way. Some printers have a scan feature.
And how can I send you, via email or?
Oh, well, if you're doing the scan thing, everybody will do it the same way. There's a program, there's going to be this place on Canvas, and it will say, upload your working here. I tell you what, I could show you.
Yeah, but because I was looking for uploading from my.
It's not there yet because we haven't got to it. I'm going to show you my other classes version of that, since they've done the test. I can show you what kind of what it's going to look like, and that might make you feel a little bit more comfortable about it. Okay, let's go to my dashboard. I'll do one of my calc classes there, this calc class here. what you're going to have, let's close this off, is you're going to have something here that will say midterm information. And I'll have a file here that just tells you all the good stuff in case you missed any of it. This video shows you how to do a program called Adobe Scan. That's how you can use your camera to do it. And this is another one that shows you. And you see this guy here, upload working. You're going to have upload working here, right? Yours will look like this. And when you click on this, you'll have the ability to hit a little link, publish it, and it's done. So you basically, you have it as a PDF and you just upload it. If you've ever done, I don't know, some of you ever done English projects where you had to upload your English thing? Ever done that? It's just like that, if you have done that. On Thursday, I'll have your version of that so you can actually physically see what I'm talking about, okay? And right now it's kind of vague in general. But see this guy here? You'll have one that will say the PDF of the midterm is here. And when you click it, this is my calc class, but you see, you'll have questions and you scroll through them.